Okay, welcome everybody. Today we're going to watch a video on section 2.1, which is called Polynomial Functions, and we'll start off with what a polynomial function is. So the standard form of a polynomial function has the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and then there's a bunch of terms where the power of x decreases, plus a sub 1 x to the 1 plus a constant term a sub 0. Now, the subscript on each of these coefficients, for instance, if we look at the coefficient on the term with the highest power of x, a sub n, the subscript n is just telling us that that is the coefficient on the term that contains x to the n. Okay, so the subscripts just match up with the powers of x. We also say that this is an nth degree polynomial when a sub n is not equal to 0. Essentially x to the n in that case is going to be the highest power of x, and then the power is what gives us the degree. And we'll do an example shortly after a few more terms. The a sub 0, a sub 1, all the way up through a sub n minus 1 and a sub n are what are called the coefficients of the polynomial. And a sub n x to the n, the term that has the highest power of x appearing, is also what we call the leading term. So now let's take a look at an example, just to become familiar with the terminology. So example 1, let's find the degree and leading term of f of x equals 2x times the quantity in parentheses 4x minus 2x cubed plus x squared minus 2x. So the first step is to distribute the 2x and put the polynomial in what we call the standard form, and that is just where the from left to right the powers of x are in descending order. Okay, so the first step then was to distribute this 2x through the parentheses, and you would get an 8x squared minus 4x to the fourth, and then the terms on the outside, you still have x squared minus 2x. The next step will be to combine any like terms. So notice we have two x squared terms. We have the 8x squared and the x squared. So now the polynomial would become f of x equals, and what we'll do is we'll write the term with the highest power of x first. That's going to be our leading term. So I have a minus 4x to the fourth plus 9x squared minus 2x. So that would be the standard form. Okay, the coefficients would be minus 4, 9, and negative 2. So those are the three coefficients. And the leading term is negative 4x to the fourth. That is the term that has the highest power of x. We would say that the leading coefficient then is negative 4, and the degree of this polynomial, so the degree of f, is 4, because that's the highest power of x appearing in the standard form. Okay. Next, what we want to do is we want to identify some of the graphical properties and characteristics of polynomials. So before our next example, what I want to do is I want to take that same f of x. Actually, let me write that up here. So if we take that same polynomial from before, f of x was minus 4x to the fourth plus 9x squared minus 2x. Okay. And then what I'm going to do is I'm also going to look at a function g of x, which is just given by the leading term of f, so minus 4x to the fourth. Okay. And what I want to do is I want to see what happens to the outputs of f and g when the values of x become large in absolute value. So what I'm going to do now is I'm going to make a table. Our x values are going to increase by powers of 10. So we'll just look at x equals 1, 10, 100, 1,000, and 10,000, and we will compute the output values of f and g using those input values x. So I'm going to, off to the side, plug all these in my calculator. I'm going to fill out the table, and we're going to notice something as x becomes increasingly larger. Okay, so I plugged 1, 10, and 100 into f of x, my original polynomial, and then I plugged 1, 10, and 100 into the leading term, negative 4x to the fourth. And what you would maybe notice is, for the first few values, maybe x equals 1, 2, 3, f of x and g of x might be, they might not seem so similar, but as you increase the value of x from 10 to 100, and if I was to increase and keep plugging in 1,000 and 10,000, I don't have room in my table to write those in. But you're going to notice that the outputs of f and g are going to start becoming almost similar. And what this seems to suggest is that if I want to know how a polynomial behaves for large values of x, I just need to look at the leading term. So the first note or fact is that the end behavior, okay, what happens to f of x as x gets large in absolute value, is going to be the same behavior as g of x when x becomes large in absolute value. So what I'm going to do is, if I open Desmos, I can take a look at our original graph, and I can also compare that to just the graph of the leading term. So, just a moment, I lost connectivity to the desktop. Okay, so now I have my connectivity to my desktop back. Here we are on Desmos. The red graph is the graph of our polynomial f of x minus 4x to the fourth plus 9x squared minus 2x. And the graph in blue is just the graph of the leading term. Now, notice that, for values of x close to 0, the outputs of these functions are very different. But what's going to happen is, as I zoom out more and more, okay, what you would notice is that the graphs are going to become almost indistinguishable. Okay, so for larger values of x, essentially the outputs of these functions are very, very, very close. So once more, here's our function f of x, negative 4x to the fourth plus 9x squared minus 2x, and the larger that x gets in absolute value, either more and more positive or more and more negative, the graph is going downward on the ends, which means that the end behavior, the way I would describe it, is as x gets larger and larger, the outputs of the function x are becoming more and more negative, okay, or approaching minus infinity. So the way that you can write or describe the end behavior is as such. So the end behavior, we would say, as x gets large and positive or approaches infinity, okay, so that's what this means right here. So this first part right here means as x approaches infinity. Okay. The next piece right here means f of x approaches negative infinity. So what I would do is up here I would just write a minus infinity. So this just means as x gets really large and positive, the graph of f of x is going to go downward. So we say f of x approaches minus infinity. So this expression here symbolically, okay, means in words as x approaches infinity, f of x also approaches minus infinity. And again, you can see it on the graph. As x is going to get large, the outputs or the y values are going to become more and more negative. And we can also say this as x approaches minus infinity. So as x is if you look at the graph, as x gets more and more negative, again, the values of the function are becoming more and more negative, so we can say f of x approaches minus infinity. Okay? Okay, so what I said before a couple slides ago was that the end behavior of a polynomial function is the same as the end behavior of the leading term. So there's going to be four possibilities for what the general shape of the graph of the leading term is going to look like. One possibility is, so we're looking at, y equals a sub n x to the n. Okay. If n is even and a sub n is greater than 0, the graph is going to essentially look like x squared. So it's going to look like a parabola opening upward. If n is even, but the leading coefficient is negative, you can even just think about taking the graph I just drew and doing a reflection over the x-axis. Okay, in this case, your graph is going to look something like this. Okay. And then forgive my poor artistic skills. Okay. But in the case that the power on the leading term is even, if the coefficient is positive, it opens up. And in the case that n is even, it's going to open down. Okay. And what we can do is, given a polynomial, we can look at the leading term, we can draw a rough sketch of its graph, and that'll help us do the end behavior. We'll see an example in just a moment. Now, what if the power on the leading term is odd? So again, if it's y equals a n x to the n, if n is odd and a sub n is positive, think about something like x cubed as an example. What the graph is going to do is it's going to start in the third quadrant, it's going to come through the origin, and it's going to increase. Okay, so there's the x and y axis. Okay, so that's what a general leading term would look like, where the power on x is odd and the leading coefficient is positive. Now if n is odd and the leading coefficient is less than 0, the graph is just going to essentially be the previous graph reflected again over the x-axis. And this time it's going to decrease. Okay, so it's going to decrease from the second quadrant through the origin down into the fourth quadrant. So let's return to and look at one more example. Okay, so let's find the end behavior of f of x and g of x, where f of x is minus 3x cubed plus 4x squared minus 7, and g of x is 4x to the 8th minus 6x to the 4th plus 3x cubed minus 2x. Okay, so for a, what you can notice is the leading term. Oops. The leading term is negative 3x cubed. And a rough sketch of the graph of minus 3x cubed, since the coefficient is negative and the power on x is odd, the general shape of the leading term is going to look like this. So we can say, as x goes to infinity, so x becomes more and more positive, the graph is going to go downward. So we can say f of x approaches minus infinity. And as x approaches negative infinity, so as it becomes more and more negative, the graph is going to be going upward. The outputs are becoming more and more positive, so we would say f of x is approaching positive infinity. And there's our end behavior. For part B, the leading term is 4x to the 8th. And the graph of 4x to the 8th generally looks like it almost looks like x squared. It's been, stretched by some factor, okay, away from the x-axis, but the general shape is it's going to be opening upward on both ends. So the end behavior then, we can say as x becomes more and more positive, the outputs of g of x, so the y values, notice the graph is going upward, so if you look at this piece right here, as x gets more and more positive, so as we move more and more to the right, the graph is going to keep increasing, going upward. So we would say g of x is also approaching positive infinity. And then as x becomes more and more negative, okay, so x is becoming more and more negative, the outputs, the g of x values are becoming more and more positive in that case. So we would just say g of x approaches positive infinity as well. Okay, so if the coefficient, if the power on the leading term of x is even, the end behavior is going to be the same on both ends. It just depends on the sign of the coefficient, whether or not you're approaching infinity, the function's approaching infinity or minus infinity. But that is how we would describe our end behavior. So the next thing we're going to do, I've just opened the textbook here, we're going to talk about absolute maximum and minimums. So the absolute maximum and minimum outputs or y values of the graph of a function f. And then we're also going to talk about something called local maxima and minima. Okay, so make sure before you move on you read this slide carefully. The absolute maximum value of f, so if I enter my drawing mode here, so the absolute maximum of f is just the largest output of f on the entire domain. Okay, so f of c, if that's the largest output of f on the entire domain, we say f of c is an absolute maximum. And let's see, if f of c is the smallest output of f, we say f of c is an absolute minimum value. Now there's also a notion of local maximum and minimum values. So if you can find a little interval on your domain so that f is defined and c is strictly inside of that interval, if f of c is greater than all the other function values f of x, for all x in that interval, we say f of c is a local maximum value of f. And if f of c is less than or equal to all the other values of the function f of x in some interval containing c, f of c is the local minimum. Okay, so I think maybe the best way to go through this is through an example. Okay, make sure you read through these definitions carefully. The local maximum and minimum values, all those are essentially saying is you could zoom in far enough on a graph and you'd like a local maximum, you would zoom in on a point, and if you can zoom in far enough so that on that restricted interval or that zoomed in piece of the graph, f of c would be a local maximum value if it's a maximum on that small little zoomed in piece. So for example, if I look here at figure 2.4 in the textbook, okay, we're going to go ahead and find our absolute max and minimums if they exist, and we'll also find any local maximum and minimums. So usually the first thing I do is I come through and I essentially kind of find what I would call peaks and valleys. So if you just looked at, say, this piece of the graph, okay, so now I have zoomed into some interval where I have a point that's greater than or equal to all the y value is greater than or equal to all the other function values. Okay, so you could say, first we'll write the local maximums. So the local maximum values are, so if you zoom into that little piece of the graph in the green box, the maximum value in that little piece would be 0. Okay, and then if you look closely at the graph, there should be another place where you have a local maximum value, i.e. a place you could zoom in far enough so you have a maximum. Okay, there's also another piece right here. Okay, so if I zoom in far enough, my graph would just look like that piece. And you'll notice you have a little maximum value there. That would be a local maximum. And the y value there is approximately, I don't know, let's say it's like 2.2. Okay, so those are the local maximum values. But if you look at the entire graph, that point I just filled in, okay, this point up here at positive 2.2 roughly. Okay, so again, these are the y values, the local maximum values. If I look at this point up here, in fact, it might even be a little bit more closer to 2.1, right? If we come over to the, if I came over to the y-axis there, we'd be at about 2.1. Now, 2.1 is the largest y value on the graph, so this is also the absolute maximum. Okay. The local minimum value, okay, I can zoom in, let me erase part of my piece over here. Here's a part of the graph I could zoom in, and then if I zoomed in on just that little piece, we would have a local minimum value. Okay, the y coordinate of this point is about negative 1.5, so the local minimum is approximately negative 1.5. Okay, now the next thing you do is ask yourself, is there any absolute minimums? Is there any point on the graph that is less than or equal to the y values of any other point on the graph? Now you might be tempted to say that this open circle down here would be an absolute minimum value, but it's actually not really a point on the graph. If you followed along this piece and you tried to get closer and closer to that open circle, you could really get as close as you wanted to, but never get to that open circle. So actually there are no absolute minimums. Okay, so the thing to remember is if you have a lowest or highest point and it corresponds to an open circle, you won't have any absolute maximum or minimums. Okay, but in this case of maximum values, if you look at this point over here, okay, at just over, x equals 2.2, let's say, the y value there is approximately 2.1. That is a point on the graph since it's not filled in with an open circle, so we actually do have an absolute maximum, but we do not have an absolute minimum because the lowest point is an open circle. So again, we had kind of two points where a local maximum occurred. Okay, and then this point up here that actually also gave you an absolute maximum, but you only had one absolute minimum. Let's use a different color. There's only one absolute minimum down here, and then since the lowest point here is an open circle, we have no absolute minimums. Okay, so we have a local min, but we have no absolute min. And then lastly, this video is getting a little bit longer than I wanted to. I want to keep it up under 30 minutes. But the last thing I want to do is talk about increasing and decreasing functions. Okay. Now, if the graph of f rises as you read it from left to right on an interval a, b on the x-axis, then f is increasing on that interval a, b. And if the graph of f of x falls from left to right on an interval AB on the x-axis. And actually, sorry, I should be careful. My interval should really be an open interval on the x-axis. Then f is decreasing on the interval AB. Okay, so again, if you can find an interval on the x-axis where the function goes up from left to right, the function's increasing on that interval, and if you find an interval where the graph falls from left to right, then you say f is decreasing on that interval. Okay, so let's take a look at this example from the text again, and we're going to find the intervals Okay, so f is going to be decreasing on, so if you look at the blue part of the blue graph, above that is the, I've shaded in purple the interval on the x-axis, and it looks to be decreasing from about -2 to x equals negative, So I have to pause here because I just caught myself in a little mistake, because it's actually, if you look at where you start increasing, the second red piece, to me that actually looks closer to minus 0.2. Okay, and that's also where the first blue piece would stop decreasing, so actually this should have also been a minus 2.2. Sorry. 0.2. Okay, so that was my mistake. Okay, so it's increasing from -3 to -2, but then it starts decreasing from -2 to about -0.2. It also increases from about -0.2 to x equals 2.2, so that's this interval. And then it would start decreasing again at positive 2.2 until the graph finally ends at positive 3. Okay, so the assignment for Friday is to take the function f of x equals 1/4 x to the 4th minus 2x squared minus 2. Part A, find the end behavior of f. You should be able to do that by hand without using technology. Part B and C, okay, so these ones, go ahead and use Desmos or some other graphing technology, and you should be able to find the local extreme values, which would be the local max and mins, and the absolute extreme values, the absolute max and mins, if they exist. Okay, and then part C would just be find the intervals of increase and decrease. Now, make sure you're careful, just a clarification, this is intervals on the x-axis. Okay, so you want the x values that the function would be increasing or decreasing on. This will be due on Friday at the beginning of class. Hopefully it should only take you about just under 30 minutes to watch the video, and maybe about hopefully 15-20 minutes to get through this. We can discuss the problem in class as well on Friday, but I would like everybody to turn their work in at the beginning of class. Okay, thank you everybody for tuning in. Sorry about writing a little bit sloppy and quick at the end. I just wanted to keep the video under 30 minutes, but again, hopefully everybody watches the video. Bring your work on this problem to class on Friday. Thank you.